We track an athlete on a circular path with a 7-meter radius. The athlete completes one full revolution in 20 seconds. Based on ground covered, speed is 2.2 meters per second. But simultaneously, the math dictates their velocity is exactly 0 meters per second. The object was in continuous, high-speed motion for the entire duration of the test. How can a system in constant motion yield a net velocity of 0? The anomaly occurs because everyday language conflates two different mathematical concepts. Outside of physics, speed and velocity are used interchangeably. In physics, we rely on a core bifurcation to classify measurements: scalar quantities versus vector quantities. Resolving this paradox requires mathematically separating the physical effort of movement from the net effect of that movement. We establish our analytical framework starting with the first metric, which is speed. Speed is defined strictly as the rate at which an object covers distance over time. It is a scalar quantity. A scalar possesses magnitude, a numerical value, but it is entirely blind to direction. It only measures how much. Applying this scalar lens to the athlete on the track, we only care about the total accumulated path length. We execute the source math by calculating the circumference of the 7-meter radius circle, which unspools into a straight line to give us a total physical distance of roughly 44 meters. We complete the scalar calculation by dividing that 44-meter distance by the strict 20-second time limit, proving the calculation of 2.2 meters per second. This establishes the absolute rule of scalar speed. If an object is moving at all, its speed must be a positive value. Think of a car driving along a highway at a steady 60 kilometers per hour. That positive number reflects continuous motion. Scalar metrics like speed are excellent for quantifying total energy spent, but they are insufficient for calculating position because they ignore spatial orientation. We will now shift the analytical framework to the second metric, velocity. Velocity is defined as the speed of an object moving in a specified, measurable direction. It is a vector. A vector is a quantity that demands two distinct properties simultaneously: magnitude and directional orientation. Revisiting the car on the highway, that 60 kilometers per hour is merely the raw scalar data. We introduce the vector requirement by locking the car's movement to a specific coordinate axis. The addition of that directional orientation, say 60 kilometers per hour north, transforms the raw speed into a true velocity vector. This property means that changing direction alters the velocity vector, even if the speedometer remains perfectly static. Because vectors exist on coordinate grids, velocity can possess positive values, negative values if the object moves backward along an axis, or exactly 0. Vector metrics map an object's absolute orientation in space. This is the foundational tool required to crack the circular track paradox. We return to the original anomaly: the athlete running the 20-second circular track at 2.2 liters per second. To calculate velocity, we must swap out the scalar variable of distance for a vector variable, displacement. Displacement is strictly defined as the net spatial change in position from the exact starting coordinate to the exact ending coordinate. Observing the athlete's motion again, the scalar distance, traced here along the path, accumulates endlessly. But the displacement factor calculates only the straight line distance from the origin. Halfway around the track, the displacement factor reaches its maximum magnitude, stretching directly across the circle's diameter. As the athlete continues past that halfway point, the net displacement actually begins to shrink. At the exact 20-second mark, the athlete returns to the exact starting coordinate, and the displacement factor vanishes. The final velocity calculation is straightforward. 0 meters of displacement divided by 20 seconds equals precisely 0 meters per second. Despite the immense physical effort expended along the path, the mathematical net effect of the journey through space is exactly 0. This matrix provides a formalized comparative analysis of the two systems, establishing our final kinematic rulebook. First, the definitional rule. Speed tracks the total path of the journey, while velocity tracks the net spatial displacement. Second, the quantity rule. Speed is limited to a scalar magnitude, while velocity operates as a vector in a coordinate space. Third, the zero-state rule. Speed cannot be 0 if a system is active, but velocity easily drops to 0 upon returning to an origin point. Finally, the value range rule. Speed is locked to positive integers, while velocity can register as positive, negative, or zero based on its directional axes. Physicists refuse to compromise on having two separate metrics to answer the simple question of how fast an object is moving. Scalar speed is necessary because it prevents us from ignoring the real-world time and energy spent traversing a path. Vector velocity is necessary because it prevents us from losing track of an object's absolute position in the physical universe. Mastering the foundation of kinematics requires moving beyond a single definition of movement to track both the physical path taken and the resulting change in position.